The paper introduces a discrete version of weighted Morrey spaces and discusses their inclusion relations. It also establishes the boundedness of discrete weighted Hardy-Littlewood maximal operators on discrete weighted Lebesgue spaces by deriving a discrete Calderón-Zygmund decomposition for weighted L1 sequences. The authors then discuss the necessary and sufficient conditions for the boundedness of the discrete Hardy-Littlewood maximal operators on discrete weighted Morrey spaces, particularly for discrete power weights. This work builds upon previous research on classical Morrey spaces and their weighted variants, extending the understanding of discrete operators and spaces. In harmonic analysis, the study of weighted estimates for discrete operators is crucial. A key operator in this context is the discrete Hardy-Littlewood maximal operator, defined as the supremum of averages of a function over all cubes in Z(d) containing a given point. This operator is bounded on discrete Morrey spaces, which are spaces of functions with bounded norm. This paper addresses the question of whether Theorem 1.3 can be generalized to weighted sequences in discrete weighted Morrey spaces when d equals 1. To tackle this problem, we introduce discrete weighted Morrey spaces and discrete AP weights, which are essential in harmonic analysis. The discrete Hardy-Littlewood maximal operator is a fundamental tool in our investigation. We employ the discrete Calderón-Zygmund decomposition, a powerful technique for obtaining strong and weak type inequalities for the discrete weighted Hardy-Littlewood maximal operators on discrete weighted Lebesgue spaces. This decomposition is critical in deriving bounded results on Z. Our main objective is to establish the necessary and sufficient conditions for the boundedness of the discrete Hardy-Littlewood maximal operators on discrete weighted Morrey spaces. We achieve this by exploiting the properties of discrete AP weights and the discrete Calderón-Zygmund decomposition. The organization of this paper is as follows. We introduce the discrete weighted Morrey spaces, discrete AP weights, and the discrete Hardy-Littlewood maximal operator, followed by the discrete Calderón-Zygmund decomposition and its applications in obtaining strong and weak type inequalities. Finally, we present the main results, highlighting the importance of the discrete Calderón-Zygmund decomposition for the boundedness of the discrete Hardy-Littlewood maximal operators on discrete weighted Morrey spaces. The discrete weighted Morrey space and discrete Muckenhaupt class are introduced, where a discrete weight is defined as a sequence of positive real numbers. The discrete weighted Morrey space, denoted by LPQ, omega, V, consists of sequences X with the norm given as the supremum over all M and N of the average of X, K, P over Sm, N, weighted by omega, K, and V, K. This space is a Banach space with respect to this norm. In particular, when the weight V equals omega, the space reduces to LPQ, omega. And when 1 is less than or equal to P less than Q equals infinity, it simplifies to LP infinity, omega, V. These special cases highlight the versatility and range of the discrete weighted Morrey space in various mathematical contexts. Proposition 2.4 establishes critical relationships between two discrete weighted Morrey spaces, providing three key claims. Firstly, if 1 is less than or equal to P is less than or equal to Q less than infinity and omega, K, is less than or equal to CV, K, for every K element of Z, then LP, Q, V, omega, is a subset of LP, Q, omega, V, with a bounded norm. This is demonstrated by showing that parallel X parallel LP, Q, omega, V, is less than or equal to C parallel X parallel LP, Q, V, omega, for every X element of LP, Q, V, omega, utilizing the given weight inequality omega, K, is less than or equal to CV, K, to establish inequalities 2.1 and 2.2, leading to the desired norm bound. Secondly, if 1 is less than or equal to P less than Q equals infinity and V equals omega, then L infinity is a subset of LP, infinity, omega, with a bounded norm. This is proven by showing that parallel X parallel LP, infinity, omega, is less than or equal to parallel X parallel L infinity for any X element of L infinity. Lastly, if 1 less than P less than Q less than infinity and V equals omega, then LQ, omega is a subset of LP, Q, omega, with a bounded norm. Although the proof is omitted, It is stated to follow immediately from Holder's inequality. These results will be useful in studying the relationships between two discrete weighted Morrey spaces. The authors introduce the weighted weak-type discrete Morrey space, denoted by WLP, Q, omega, as a set of sequences taking values in R(s), defined for 1 is less than or equal to p is less than or equal to q less than infinity, where omega is a discrete weight on Z. The norm of this space is given by a supremum over m element of Z, n element of n, and lambda greater than 0, involving the discrete weight omega and the sequence x. Notably, proposition 2.6 establishes that LP, Q, omega, is a subspace of WLP, Q, omega, with a bounded norm, where the proof relies on applying Holder's inequality and the definition of the weighted weak-type discrete Morrey space. The authors also introduce the discrete Muckenhaupt class, a class of discrete weights on Z. A weight omega belongs to the discrete Muckenhaupt class A1, Z. If a certain supremum, taken over all finite subsets J of Z, is finite. For 1 less than p less than infinity, a weight omega belongs to the discrete Muckenhaupt class AP, Z. If another supremum, involving the weight omega and the interval J, is finite. The norm of the weight omega in AP, Z, is denoted by omega, AP, Z. The authors define A infinity as the union of all AP, Z, for 1 is less than or equal to p less than infinity. Furthermore, they highlight that some basic properties of discrete AP weights can be proven using similar arguments as in the real-line case, providing select proofs for completeness. This framework lays the groundwork for further analysis, building upon the properties of these discrete weight classes. In this section, the authors introduce two key propositions that establish the equivalence between certain conditions for discrete weights on Z. The first proposition, proposition 2.8, states that a discrete weight omega is in A1 if and only if it satisfies a specific boundedness condition involving the sum of its values over a bounded interval J. This result is pivotal for understanding the properties of A1 weights and their role in harmonic analysis. The second proposition, proposition 2.9, focuses on the AP class of weights for 1 less than p less than infinity. It asserts that a discrete weight omega belongs to AP if and only if it meets a particular inequality related to the sum of x, k, over a bounded interval J. This result provides insight into the nature of AP weights and their relationship with the discrete Hardy-Littlewood maximal function. The proof of proposition 2.9 begins by showing that I implies E, using H. Diaresis-Older's inequality and the definition of AP. Then, it demonstrates the converse, i.e., E implies I, by choosing x, k, equals omega, k, caret 1, p1, and applying the given inequality from E. This leads to the conclusion that omega element of AP, completing the proof. These propositions contribute to a deeper understanding of the properties and behaviors of different classes of discrete weights, which are crucial in various areas of harmonic analysis and its applications. They provide researchers with tools to analyze and characterize these weights, ultimately aiding in the development of new techniques and results in the field. The authors present proposition 2.10, deduced from propositions 2.8 and 2.9, involving the Hardy-Littlewood maximal operator. Let omega element of AP, where 1 is less than or equal to p less than infinity, lambda element of Z plus, m element of Z, and n element of n define lambda Sm, n as the set of k element of Z such that Km is less than or equal to lambda n. For each n element of n, consider a collection of disjoint intervals in of cardinality 2n. For any interval I element of in and n is greater than or equal to 2, define nLi, nRi, and 2n1, I as subsets of I. The proposition asserts that there exist constants c greater than 0 such that the summation of omega, k, over k element of lambda Sm, n is bounded by a constant multiple of lambda p times the summation of omega, k, over k element of Sm, n. Additionally, the summation of omega, k, over k element of nLi, k element of nRi, and k element of 2n1, I are each bounded by a constant multiple of np times the summation of omega, k, over k element of I. The proof of the first part is provided for the case p equals 1, using definition 2.7, showing that the summation of omega k over k element of lambda sm n is bounded by a constant multiple of lambda sm n times the infimum of omega k over k element of sm n, which is further bounded by a constant multiple of lambda sm n times the summation of omega k over k element of sm n. The authors establish inequalities for the summation of weights omega k over the set lambda sm n, where sm n is a subset of integers. Specifically, they show that when p greater than 1, the inequality lambda sm n is less than or equal to c n airy summation k element of sm n omega k caret 1 p holds, where c is a constant. This is proved by applying proposition 2.9, which provides an upper bound for the weighted sum of xsm n k over k element of lambda sm n. The authors also derive a series of inequalities, ultimately leading to the bound n airy summation k element of lambda sm n omega k is less than or equal to 3/2 c lambda caret p n airy summation k element of sm n omega k. The proof of proposition 2.10 is then completed, and a remark is made that if omega is defined as c, then c element of AP, p is greater than or equal to 1, and particularly, if omega is defined as 1, then the counting measure is a doubling measure. The authors then introduce the concept of discrete AP, n, weights, analogous to discrete AP, z, weights, and discuss the relationship between them. Proposition 2.12 states that if omega element of AP, n, 1 is less than or equal to p less than infinity, then the weights omega, element of AP, z, 1 is less than or equal to p less than infinity, with a specific bound on the AP, z, norm. The proof of this proposition involves considering bounded intervals J subset of Z and dividing them into subsets J1 subset of Z minus and J2 subset of N. The authors then apply the definition of AP, N, weights to obtain the desired bound. The authors investigate the Hardy-Littlewood Maximal operator, focusing on estimating the quantity J, n airy summation K element of J omega, K, ard L omega minus 1, ard L infinity. By applying proposition 2.8 in equation 2.3, they derive an upper bound for this quantity, involving the maximum values of omega k over two subsets J1 and J2 of J. The upper bound is decomposed into two terms, A and B, where A is obtained by applying the inequalities minus J1 is less than or equal to J, and J2 is less than or equal to J, and B is derived from the assumption omega element of A1, n. The term gamma 1 is introduced, representing the sum of two maximum values of omega k over J21 and minus J11, respectively. To estimate gamma 1, the authors consider two cases. Case I, where minus J1 subset of J2, and case 2, where J2 subset of minus J1 union 0 equals J3. In both cases, they establish an upper bound for gamma 1, proportional to ard L omega, ard La 1, n. By combining the estimates for gamma 1 in both cases, the authors arrive at the final estimate for J, n airy summation K element of J omega, K, ard L omega minus 1, ard L infinity, bounded by 4, ard L omega, ard La 1, n. For p greater than 1, the authors further derive an estimate involving the pth power of the quantity J, n airy summation K element of J omega, K, relying on the properties of the A1, n, class of weights and the Hardy-Littlewood Maximal operator. Throughout the analysis, they leverage the relationships between the subsets J1, J2, and J to establish the desired estimates. This section of the research paper delves into the estimation of gamma 2, a pivotal component in the analysis of a specific mathematical inequality. The authors consider two distinct cases for estimation. Case I, where J1 is a subset of J2, and case 2, where J2 is a subset of J1 union 0. In case I, The authors leverage the fact that J1 subset of J2 to bound gamma 2 by a constant multiple of art L omega, art lap, n. This is achieved through a series of inequalities involving the sums of omega, k, and omega, k, caret 1, over different sets of indices. In case 2, the authors utilize the fact that J2 subset of J1 union 0 to again bound gamma 2 by a constant multiple of art L omega, art lap, n. The reasoning follows a similar pattern as in case I, with the main difference being the change in the index sets for the sums. Combining the estimates from both cases, the authors obtain the final bound for gamma 2, which is expressed as an inequality involving the sums of omega, k, and omega, k, caret 1, over the set J, along with the constant C2, p and the function AP, n. This result is crucial for the overall analysis presented in the paper, as it helps to establish a connection between the given mathematical objects and their properties. The Hardy-Littlewood Maximal operator is a fundamental concept in harmonic analysis, used to study the properties of functions under the operator's action. We begin by concluding the proof of proposition 2.12, which establishes the relationships among weights AP, R+, AP, N, and AP, Z. A discrete weight omega belongs to the discrete reverse holder class RHR if it satisfies a specific condition involving the reverse holder norm of the weight over any bounded interval J in Z. This condition is crucial for understanding the properties of the operator. We also recall basic inclusion relations of Muckenhaupt classes and reverse holder classes, which are essential for the analysis. These relations include a 1 subset of AR subset of AP for 1 is less than or equal to R is less than or equal to P less than infinity. RHP subset of RHR for 1 is less than or equal to R less than P, and the existence of a constant R element of 1, infinity, such that omega element of RHR if omega element of infinity. Furthermore, proposition 2.16 states that if omega element of AP 1 less than P less than infinity, then there exists a constant epsilon greater than 0 such that P epsilon greater than 1 and omega element of AP epsilon. Using Holder's inequality, we obtain proposition 2.17, which describes the relationship between the weight of a subset S and its parent interval J in Z. This sets the stage for the introduction of the discrete Calderón-Zygmund decomposition for weighted L1 sequences, as discussed in Theorem 3.1. This decomposition is critical for establishing the boundedness of discrete weighted Hardy-Littlewood maximal operators on discrete weighted Lebesgue spaces in the following section. The paper discusses Theorem 3.1, which examines the properties of a function x under specific conditions. It states that for any positive real number t, there exists a constant c depending on p and a sequence of disjoint intervals id, consisting of maximal dyadic intervals, where the average of x relative to omega is greater than t. The proof involves showing that for every dyadic interval I in it, the average of x is bounded by quart, and that all elements not included in the union of these intervals have x n is less than or equal to t. This theorem's significance lies in its application to the study of functions and their properties, particularly in the context of dyadic intervals and their relationships. Here is the refined version of the transcript. The Hardy-Littlewood maximal operator, a fundamental concept in harmonic analysis, is defined as the discrete weighted Hardy-Littlewood maximal operator M omega. This operator acts on sequences x equals x, k element of Z subset of R and discrete weights omega, producing a new sequence M omega x with elements given by the supremum of ratios of weighted sums over dyadic intervals Sm, n. The discrete weighted Hardy-Littlewood maximal operator plays a crucial role in establishing weighted estimates for discrete maximal operators. Theorem 4.2 provides two key estimates for M omega x. Specifically, if omega element of A1 and x element of L1 omega, then for every t greater than 0, the measure of the set where M omega x exceeds t is bounded by a constant times the norm of x in L1 omega. Additionally, if omega element of AP and x element of LP omega, 1 less than P less than infinity, then M omega x element of LP omega, and its norm is controlled by the norm of x in LP omega. These estimates are essential in understanding the behavior of m omega x under various conditions on the weight omega and the sequence x. The proof of theorem 4.2 involves a discrete Calderón-Zygmund decomposition for weighted L1 sequences, which enables a more nuanced understanding of the relationship between m omega x and x in terms of their norms in weighted Lebesgue spaces. To facilitate the proof of theorem 4.2, a preparatory lemma, lemma 4.4, is introduced. This lemma states that for x element of Lp omega and p greater than 0, the norm of x in Lp omega can be expressed as an integral of the measure of the set where x, k, exceeds lambda, multiplied by lambda p1, over the positive real numbers. This result is crucial in establishing the weighted estimates for m omega x. The page begins with the omitted proof of lemma 4.4 for brevity. It then delves into the proof of theorem 4.2, specifically part I, which aims to establish the inclusion k element of z m omega x k greater than c1t subset of union I element of it 3I. Here, c1 is a positive constant dependent on p and the ap z characteristic of the weight omega. To achieve this, the authors consider an arbitrary j not belonging to the union of intervals at 3I. They aim to show that j cannot be an element of the set k element of z m omega x k greater than c1t. The proof involves choosing an interval j centered at j and introducing two dyadic intervals Rn plus 1, 1 and Rn plus 1, 2 that intersect j. Since j does not belong to the union of intervals it cannot be part of the right or left extensions of any interval I in it. This implies that both Rn plus 1, 1 and Rn plus 1, 2 cannot be any one of the intervals in it. Consequently, the weighted averages of x on Rn plus 1, 1 and Rn plus 1, 2 are at most t. By applying proposition 2.10, I, the authors derive an inequality involving the weighted averages of x on Rn plus 1, 1 and Rn plus 1, 2. This leads to the conclusion that the weighted average of x on j is bounded by c1t, thereby establishing the desired inclusion. The constants and weight omega play crucial roles in the proof, and the authors carefully manipulate the inequalities to arrive at the desired result. The proof relies on the properties of the weight omega and the ap z characteristic, which are essential in harmonic analysis. The Hardy-Littlewood Maximal operator is discussed, focusing on its properties and boundedness results. By leveraging the Calderón-Zygmund decomposition and the Hardy-Littlewood inequality, the authors establish the weak type 1 boundedness of the operator. This is achieved through a series of equations and inequalities, showcasing the operator's behavior on discrete weighted Morrey spaces. The proof is completed by deriving an estimate for the discrete Hardy-Littlewood maximal operator, demonstrating its Lp infinity, L infinity, boundedness. Here is the refined version of the transcript. Theorem 4.5 establishes a connection between the discrete weighted space Lp infinity, omega, and the boundedness of the maximal function mix. Specifically, for x in Lp infinity, omega, with 1 less than p less than infinity and omega in ap, mix is bounded in L infinity, and there exists a positive constant c such that the L infinity norm of mx is bounded by the Lp infinity, omega, norm of x, with c depending on omega. This result is proven using Holder's inequality and the definition of discrete weights ap, showing that the supremum of the averages of x over all dyadic intervals is bounded by the Lp infinity, omega, norm of x, implying the boundedness of mx in L infinity. Theorem 4.6 presents a characterization of the boundedness of the maximal function m from Lpq, omega, to Lpq, omega, in terms of the discrete weight omega. Specifically, if omega belongs to ap, then m is bounded from Lpq, omega, to Lpq, omega, for 1 less than p less than q less than infinity. Conversely, if m is bounded from Lpq, omega, to Lpq, omega, then omega belongs to aq. Notably, when omega is identically equal to 1, theorem 4.6, I, reduces to a known result from the literature. The proof of theorem 4.6 relies on two auxiliary lemmas, lemmas 4.8 and 4.9. Lemma 4.8 provides an estimate for the LPQ, omega, norm of m omega x in terms of the LPQ, omega, norm of x, where omega in infinity and x in LPQ, omega. This is proven using discrete Holder's inequality, theorem 4.2, e, and proposition 2.10, I. Lemma 4.9 states that if m is bounded from LQ omega to LPQ, omega, for 1 less than p less than q less than infinity, then omega belongs to AQ. The section discusses the Hardy-Littlewood Maximal operator, focusing on the proof of theorem 4.6. It begins by stating that if omega is in AP, there exists epsilon greater than 0 such that omega is also in AP epsilon. The operator's boundedness is demonstrated using Holder's inequality and the definition of weights. The discussion highlights the connection between the operator's boundedness and the properties of the weight function omega, including its relation to discrete power weights. The section concludes by emphasizing the significance of the weight function's properties in determining the boundedness of the operator. The discrete Hardy-Littlewood maximal operator is bounded on LPQ, omega, if and only if -1 less than beta less than q -1. This theorem can be proven by first classifying symmetric intervals into 3 types: I, 2, and 3. Proposition 4.12 states that if U is doubling, the supremum can be restricted to symmetric intervals of types I and 2 for a value equivalent to ARD-LX, ARD-LLP, U, omega. If U also satisfies a specific condition involving a less than 1 and C independent of n, the supremum can be further restricted to type 2 intervals. Finally, if 1 less than p less than q less than infinity, omega element of AQ, and U equals omega 1 minus p, q, the supremum can be taken only over type 2 intervals. The proof of this proposition follows from the properties of AQ and RHR spaces, as well as the relationship between P, Q, and R. The Hardy-Littlewood maximal operator, a fundamental concept in harmonic analysis, is the focus of this section. The authors delve into its properties and boundedness in various function spaces. They present a crucial proposition, proposition 4.13, that outlines the necessary conditions for the boundedness of the Hardy-Littlewood maximal operator between weighted Lebesgue spaces. Specifically, the authors demonstrate that if the operator M is bounded from LP, omega, to LQ, omega, then the weight function omega must satisfy certain properties related to its exponent beta. This proof involves several steps, including the use of a specific function x defined as the characteristic function of a set S0, n, and another set S defined as the union of sets Sm, L with specific properties. By analyzing these sets and their relationships, the authors derive an estimate, equation 4.5, that leads to the conclusion that beta greater than 1. They also utilize the result from a previous theorem, theorem 4.6, to obtain another estimate, which combined with the first one, yields the desired range for beta 1 less than beta less than q1. Furthermore, the authors reference a lemma found in a previous work, 7, lemma 2.12, that provides further insights into the properties of the Hardy-Littlewood maximal operator in the continuous setting. The same methodology used in the proof of this lemma can be applied to the discrete case discussed in this paper. This section of the research paper offers a detailed exploration of the Hardy-Littlewood maximal operator, shedding light on its boundedness and properties in weighted Lebesgue spaces. It provides valuable insights for researchers working in harmonic analysis and related fields. The proof of theorem 4.11, a key result in the study of mathematical inequalities involving sequences and their properties, is presented. This theorem states that for a non-negative sequence x equals x, k, k element of z, under specific conditions on the parameters p, q, and beta, the sequence belongs to the class AQ. The class AQ is defined by its relationship with the Hardy-Littlewood maximal function middlesex, k, which measures the local size of a sequence at each point. To establish theorem 4.11, two lemmas, lemma 4.14, I, and E, are introduced, providing upper bounds for the sum of the maximal function over symmetric intervals Sm, n and S0, n, respectively. These lemmas are crucial in proving the necessity and sufficiency of the conditions stated in theorem 4.11. The proof of Theorem 4.11 involves considering two cases. When S is a symmetric interval of type 1, Sm, n, and type 2, Sm, n. For type 1 intervals, the Hardy-Littlewood maximal function is used to obtain an upper bound for the sum of the maximal function over Sm, n. For type 2 intervals, a similar approach is employed, with an additional step involving another symmetric interval S, that contains S. This allows the establishment of the desired inequality and proves the theorem. The proof also involves applying the results from the lemmas and utilizing the properties of the Hardy-Littlewood maximal function to derive the required estimates. The final inequality, 4.9, demonstrates the sufficiency of the conditions in Theorem 4.11, completing the proof. This section presents a detailed analysis of the mathematical tools and techniques used to establish the main result of the paper, highlighting the importance of understanding the relationship between sequences, their maximal functions, and the parameters p, q, and beta in determining whether a sequence belongs to the class AQ. The Hardy-Littlewood maximal operator's boundedness in weighted Morrey spaces is discussed, focusing on symmetric intervals of type 1, type 2, and type 3. Estimates are provided for each type, utilizing the maximal function mx2, weight function omega, and parameters p, q, n, and n. The main result, Theorem 4.11, proves the operator's boundedness in these spaces. This is achieved by considering various cases for symmetric intervals and applying appropriate estimates. The necessity of a discrete setting for future work is also emphasized. The authors plan to investigate the validity of conclusions under a discrete setting in their next article, building upon the work of Tanaka and Nakamura Sawano Tanaka on necessary and sufficient conditions for boundedness on weighted Morrey spaces LP, LO. The refined version. This page provides a detailed overview of the research paper's conclusion and acknowledgement section, along with an extensive list of references. It highlights the significant findings and novel ideas presented throughout the study, emphasizing the technical accuracy and depth of the content. The text maintains a highly technical and professional tone, ensuring that key terms, concepts, and methodologies are explained with precision and clarity. The Hardy-Littlewood maximal operator is a cornerstone in harmonic analysis, and this section delves into its properties and applications. The authors discuss various aspects of the operator, including its boundedness and relations with Muckenhaupt and Gehring classes. They also explore its connections with fractional Hardy-Littlewood maximal operators and Morrey spaces. Key papers that contribute to the understanding of the Hardy-Littlewood maximal operator are highlighted, such as 19 and 20, which provide insights into its higher summability and discrete weighted inequalities. Additionally, the authors discuss the characterizations of Muckenhaupt AP class and sharp weak bounds for discrete Hardy operators. This comprehensive overview serves as a foundation for understanding the operator's significance in modern harmonic analysis.